In this video, we're going to look at some examples of VSEPR theory. Now, this is not going to be a comprehensive review of all of VSEPR theory. If you find that you're still having trouble after reading the book and watching this video, please make an appointment to come see me. So the central idea behind VSEPR theory, or VSEPR theory, is that electron groups want to get as far away from each other as possible, because of course electrons are all negatively charged and they repel each other. So to determine the electron geometry or the shape of a molecule, we need to know how many electron groups there are. An electron group can either be a lone pair, and this is not individual electrons, these are pairs of electrons, right, the lone pairs, or a bonded atom is considered an electron group. And it doesn't matter whether that bond is a single bond, a double bond, or triple bond, it just counts as one bonded atom. And we're not interested in the terminal atoms when we're looking at VSEPR theory. We're interested in how many electron groups there are around just the central atom. All right, and then the next couple slides, we're going to look at some examples of applying VSEPR theory to determine the shapes of molecules. All right, in each of these examples, to save some time, I've already drawn the Lewis structures, but you need to be aware on quizzes and exams and homeworks, I generally am not going to give you the Lewis structure. I'll give you the formula for the molecule or ion, and then you'll have to first determine the Lewis structure. But to save time, I've gone ahead and already drawn the Lewis structures on this video. So our first example is ozone, and the Lewis structure is given here. And so if I want to determine the number of electron groups, I need to focus on the central atom. And so I count up the lone pairs and bonded electrons. And so if I look here at this left-hand electron, or oxygen, we can see that it's a double bond. That doesn't matter. This counts as just one electron group, whether it's a single bond, double bond, or triple bond. So when I look at my central atom, I have one lone pair, I have two bonded atoms, so I have a total of 3 electron groups. All right, now to determine the electron geometry, I don't have the table on this video, but if you look in your textbook or on our chapter 10 slides, you'll see the tables that tell us for every number of electron groups and for however many lone pairs and bonded atoms there are, it tells us what the electron geometry and what the molecular geometry is. You need to know this table in order to answer these problems. You won't be given that table on quizzes or exams. So if we look at that table, we'll see that if I have 3 electron groups, that electron geometry is called trigonal planar. All right, now if I have 3 electron groups, I look at that table and see that I have one lone pair, that molecular geometry, or the shape of the molecule, is different than the electron geometry. And so when I have 3 electron groups and one lone pair, that molecular geometry is called bent. Finally, for the ideal bond angle is the same for all electron geometries that are trigonal planar, and that is 120 degrees. All right. Now, what I mean when I ask, are there deviations from the ideal bond angle? When we have lone pairs, as I do in the case of the ozone molecule, they are more repulsive than the bonding electron groups. And so they tend to force the bonded atoms closer together. So while the ideal angle for all trigonal planar molecules is 120 degrees, when I have lone pairs, we do expect deviations from the ideal bond angle. And the deviations are the ideal bond angle is going to, or the actual bond angle is going to be less than the ideal bond angle. All right, on this slide, we're going to make a projection sketch of the ozone molecule that we've done on the previous slides. So a trigonal planar molecule looks like this, right? I have my 120 degree bond angles. And when I have a lone pair, I don't represent that in the projection sketch. So I'm only going to represent 1, 2 of the bonded electrons, and I'll leave off the third group, which is a lone pair. So because all of these guys are in a plane, I don't have to worry about any of my dashes or wedges. And all I have to do to draw my projection sketch is just correctly represent the 120 degree bond angle. And typically when I do projection sketches, I just draw the atoms and I leave off the lone pairs. All right, here's another molecule. In this case, we have phosphorus trifluoride. And we're given the Lewis structure. And when I count the electron groups, again, I'm just focused on a central atom. I have 1, 2, 3 bonded atoms, 1 lone pair, for a total of 4 electron groups. When I look at the table in your textbook, if I have 4 electron groups, that tells me the electron geometry is tetrahedral. For the molecular geometry, I look and see when I have 4 electron groups and 1 lone pair, I can see that that molecular geometry is called trigonal pyramidal. The ideal bond angle for a tetrahedral electron geometry is 109.5 degrees. And again, because I have a lone pair that's going to squish my bonded atoms together and decrease my angle from the ideal bond angle, I do expect deviations from the ideal bond angle. All right, now we want to draw the projection sketch. So we'll come back to PF3 in a minute with its trigonal pyramidal molecular geometry. First, I'm just going to draw a projection sketch of a tetrahedral molecule that has 4 bonded atoms, something like methane, CH4. When I draw this guy, you can see that 2 of the atoms are in the same plane as the central atom. And so typically, when atoms are in the same plane, I just use straight lines to represent those bonds. So 2 of my bonded atoms I can represent with just straight lines. Now, if these guys are all on a plane, that means this atom is coming out of the plane of the paper towards us, and this guy is going into the plane of the paper away from us. So to represent the bonded atoms that are coming out towards us, we use a wedge. So it starts small at the central atom, it gets bigger to try to represent that it's coming out towards us. And then for this one that's going away, we used a dashed line to indicate that it's going back into the plane of the paper. And so that's how I would represent or draw the projection sketch for a tetrahedral molecule. Now in our case, we have PF3, which had a tetrahedral electron geometry, but a trigonal pyramidal molecular geometry. One of these bonded atoms is replaced by a lone pair. And so when you draw the projection sketch, you could pick whichever one of these you want to and then just leave it off. When I draw these, I typically leave off the guy that I've drawn on the top here. And so if I were to draw a projection sketch for PF3, I would draw it like this. And again, I've left off the lone pairs as I usually do in these projection sketches. Okay, our next example, we want to determine the geometry of sulfur tetrafluoride, or SF4. So again, we're given the Lewis structure. This has 1, 2, 3, 4 bonded atoms, 1 lone pair on the central atom. So I have 5 electron groups. When I look at the table, 5 electron groups corresponds to the trigonal bipyramidal electron geometry. I have the 1 lone pair, so the molecular geometry will be different from the electron geometry. And in this case, if I have a trigonal bipyramidal electron geometry with 1 lone pair, the name of that molecular geometry is called seesaw. And when we get to the projection sketches on the next slide, you can see why we call it that. For a trigonal bipyramidal electron geometry, we actually have 2 different bond angles. We have 120 degrees and 90 degrees, and we'll see those again on the projection sketch. And again, because I have a lone pair, I would expect deviations from the ideal bond angle. All right, so first we'll do a projection sketch for a trigonal bipyramidal molecular geometry, and then we'll draw the projection sketch specifically for the seesaw that we have in the case of SF4. So in these trigonal bipyramidal molecules, right? So I have sort of two different atoms. In all of the other common molecular geometries, all of the atoms are essentially equivalent. In the case of trigonal bipyramidal, they're not. So these guys that form the axis are distinct from these guys that sort of form a plane in the center of the molecule here. And I can sketch this as this guy, and this guy all being in the same plane. This one's going to be coming out towards us, and this one's going to be going away. So when I sketch this, I would draw it like this. All right, now in the case of having one lone pair, for the tetrahedral and the trigonal bipyramidal, it doesn't matter which of the atoms I replace with the lone pair. In the case of trigonal bipyramidal electron geometries, it does matter, because these guys that sort of form this axis are different than these three guys that form the plane. And it turns out that the lone pairs always replace the atoms on the plane here. So when I have one lone pair, I can get rid of this guy, or this guy. And the way I typically draw this, in the case of our SF4 molecule, would be like this. And I'll usually get rid of this one. And so I keep these four, make this one a lone pair. And you can see a little bit why they call this shape seesaw. If I were to sort of rotate this guy on its side, it would kind of look like a seesaw. If you kind of look at it sideways, right, this is sort of the fulcrum, and then, you know, these are the places where you'd sit on the seesaw. All right, we'll do one more example. Okay, our final example is ICl4-. We have the Lewis structure here. I have 1, 2, 3, 4 bonded atoms, 1, 2 lone pairs. So I have a total of 6 electron groups. 6 electron groups correspond with an octahedral electron geometry. If I have an octahedral electron geometry with 2 lone pairs, that molecular geometry or shape is called square planar. The ideal bond angle is 90 degrees. Now in this case, it's different than some of the other ones. In this case, I actually don't expect deviations from the ideal bond angle, even though I have lone pairs. And when we do the projection sketch, I think you'll see why that's the case. If I had just one lone pair and an octahedral electron geometry, I would expect deviations from the ideal bond angle. So let's do the projection sketch on the next slide. All right, there are a number of different ways to represent the octahedral geometry with a projection sketch. The way I usually do it is similar to the molecule that we have here. I draw these guys all being in the same plane, and then I draw these coming out of the plane towards me, and then these going back into the plane away from me. And so for a general octahedral projection sketch, I would draw it like this. Now, in the case of having lone pairs with an octahedral electron geometry, the first lone pair, it doesn't matter where I replace, or which atom I replace with the lone pair, because each one of the 6 terminal atoms is equivalent to one another. But in the case of ICl4-, where I have 2 lone pairs, the lone pairs always go opposite one another. So I could take this one and this one, or this one and this one, or however I want to do it. Right? Now you can see that this molecular geometry is called square planar, because if I take this one and replace it with a lone pair, and this one and replace it with a lone pair, essentially I end up with a cross. So, and in this case, because I have a lone pair and a lone pair sort of symmetrically arranged around the molecule, their extra repulsiveness sort of cancels out. And so the bond angles between these guys are still going to be 90 degrees. Now, because all of these guys lie in a plane, there's no point in having to use the wedges and the dashes. So if I was going to represent this, because they're all in the same plane, all I'd have to do is draw them in the plane. Oops, I'm sorry. It's ICl4. So I is our central atom, Cl. And we have our 90-degree angles in between these guys. And because it's square planar, they all lie in a plane, don't need any wedges or dashes.